So a very good day once again. Uh, we're going to be reviewing our quiz questions in this class. So, so here's the first question, and it says, provide a descriptive note on the following digital design metrics relative to the transistor logic family. Well, it's quite simple and straightforward. Just wanted to tell us what this terms means. So we say for the fan out, fan in. Yeah. So you already know that this is the maximum number of inputs to a gate, right? And to add, we know that the TTL NAND gates provide up to 8 inputs, right? So it's the TTL, that's the transistor logic NAND gate, provides, for instance, one, two, four, or even 8 inputs, right? Then we have the fan out. Now, if the fan in specifies the maximum number of inputs to a gate, then the fan out specifies the number of standard loads that the output of the gate can drive without impairing its normal operation, okay? So this has to do with the output. So the fan out specifies hmm, and we also know that the TTL gate provides two fan out values, one for high output and another for the low output. So you can also, you want to include that. TTL gates provide two fan out value, one for high output, and then another low output. And then we have the propagation delay. Now, fine, this should be the propagation delay time, okay? So we have the propagation delay time. And we already know that it is the time required for the output of a gate to respond to a change in an input, okay? So this draws a relationship between the input and the output. And then we know related to the TTL that the average propagation time is given as the average value. Okay. So you can say the average which means the so the transistor logic is given by P sub P is the same as TPHL plus P P over 2, where PP is the average propagation and the time, then CPHL turn on delay time, and CPNH is the time of delay time. Okay. So, uh, what else do we have? The um, voltage transfer curve and the noise immunity. So let's write this. Voltage transfer curve. We already know that the voltage transfer curve is a graph of the input voltage to a gate versus its output voltage. I think that's simple enough, okay? So the voltage transfer curve is a graph of the input voltage to a gate versus its output voltage. Now, we also know that there's a threshold value in this graph when the output voltage is equivalent to the input voltage in the TTL graph. So we can just include that. So when we say in TTL, let's say the voltage by curve at which V out is the same as V in becomes the threshold voltage. Then we have noise immunity. And the noise immunity is a measure of the ability of a digital circuit to avert logic level changes on signal lines, okay? Especially when the noise causes voltage level changes, okay? So you can say this is a measure of the ability of the digital circuit to avert logic level changes. signal line and use process voltage level. So for the TTL family, let's say for TTL family, we have that DC0 is equivalent to 0.4 volts, and DC1 is also equivalent to 0.4 volts, where DC low is the same as DC0, while DC high is the same as DC1. Right? So I think that solves that problem, and then we are good to go. Okay. So is this clear? Can I get your feedback, please? Is this clear?
Yes, sir.
So let us look at the second question. This is the convolution code problem. And it says, it asks us to design the VTAB maximum likelihood decoding scheme using a 7-step trellis diagram that can be used to detect and correct errors in digital transmission. Using the connection diagram shown in Q02 or in Q2, verify the design by using the originally transmitted code words, and waits for the received bit sequence. So we have that, and then we have the connection diagram. So from this, we could develop the input-output relationship, because here we have output bit 1. Let's change this color. We have output bit 1, output bit 2, then output bit 3. So it means that this connection diagram, when fed with an input, is going to give us 3 bits as the output. Hence, we have all of these code words, 3 bits code word, right? These are code words. So now we want to use this connection diagram to verify the integrity of this received bit sequence. We want to tell if any of these code words were received in error or received accurately. So the first thing to do is to develop the input-output relationship using the connection diagram. You should know that the connection diagram depends on the designer. And once you alter the basis of the connection diagram, then the bit sequence will change in that algorithm using the VTAB maximum likelihood scheme. Let's assume the output bit 1 was SR1 and SR2, added together using the modulo 2 adder. So SR here means the shift register. Then that will alter what the first bit will be. Then let's assume, we have 1 and 2 going as the output bit 2, and then 2 and 3 going as the output bit 3. But let us use this connection diagram. So here we have that the, let's put it here. Output, let's say output bit 1 is the same as SR1 plus SR2. That's modulo 2 addition. Now, output bit, that's output bit 1. Then output bit 2 is the same as SR2 plus SR3. Yeah, this is modulo 2 addition, right? More like more like an exclusive OR, right? Then output bit 3 is the same as SR, the shift register 1, and plus the shift register 3. So with this, we could develop the truth table. And we already know that we have 3 shift registers. And that will give us how many states? 2 to the power 3 minus 1. That will be 2 to the power 2. That will give us 4 states. So it means that we're going to have 4 different states. So from state A to state B can take on, uh, uh, can switch between states, relative to this combination. So what do we do? Going by the Vita-B algorithm, then we can now develop what we have, okay? And having 4 states, so what would be the combination of our code words? So we should have about 2 to the power of 4 possible code words. That's about 16 possible code words. So let us find a way to populate this. I think I will need to use a straight line this time. Let us see if we could pull up some lines here. Let's change this color. This. Okay. So let's say we have, this. This should be sufficient. If I do this, let's take it this other way. Let's come up with this first. Have this one states. Okay. And we have our shift registers. We have about 3 shift registers. That's 1, 2, 3. Then we can have our input bit here. Then we can have our shift registers. Repeat here again. 2, 3. Then we can have our state B. We have our state B. Then we can have our output bit 1, output bit 2. Then we can have our output bit 3. So let's say we have our header here. Then, so we have about 16 possible code words. So let's see if we can have about 16 lines here. This is 1, 2, 3, 4, 2, 3, 1, 12, 13, 14, 15, and then 16. That sounds good. So, oh no. So it means we have states. Okay, let's change the color. So let's say we have our state A here, then our first shift register, our second shift register, and our third shift register. So let's assume we have our input here, Then once this is fed into the input, then what do we get? Then we have our shift register one shift. If this is the input and that fits into the shift register, then what will be the response of shift register one, shift register two, and shift register three? And then we have our state B, and then we have our output bit one, and we have our output bit two, and we have our output bit three. Okay. So we already know that we have 16 possible code words. So let us do something here. Let's move this. Okay, now let's assume we have about 16 possible code words. So that will start from uh, 0. So, um, is this. So this is not part of the table, but just for so let's say this is a serial number. So we're going to start from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. That's 16 possible code words. So if, for instance, this is, we're using 8421, yeah, 8421, okay, code. So if it's all zeros, so it means that if it's all zeros, so it means this will be, maybe they're all turned off 0, 0, 0. Then if it's one, then it means just this bit is turned on, so this will be 0. Now if it's two, so it means this is turned off, this is turned on, 0, 0, right? Now if it's three, it means this is turned on, this is 0, 0. That's then if it is four, it means just this is turned on, this is 0, this is out of turned off. And if it's five, it means one, four, and one are turned on, then all of these are zeros. And if it's six, it means this are turned on, all of these are zeros. And if it's seven, then it means this are turned on, and this is turned on. And if it's eight, so it means just this is turned on, then all of these are turned off. Now, if it's nine, it means this and this are turned on, all of these are turned off. And if it's 10, then it means this and this are turned on, then all of these are turned on. Now, if it's 11, so it means this are turned on, then this is turned off. Then how about 12? So it means this and this are turned on, while all of these are turned off. And if it's 13, then this are turned on. Now, if it's 14, so it means this are turned on, this is turned on. Then if it's 15, then it means they are all turned on. So we have our truth table in this manner, okay? And now that we have this, then we know we are moving from uh, a stage 0, but we have,
Sorry, sir, we can barely.
you can what?
I
Hello?
said we can't really hear you, sir. It's like your voice is really fast, sir.
Okay, can you hear me now? Can you hear clearly? Can you hear me
No,
clearly
sir,
now?
it's not any better.
Don't you think you want to
No, sir.
say? Can you hear me now clearly? Abiola, can you hear me clearly from your end? Who's
Yes, I can hear you.
okay? So probably you want to check your radio set, to be sure. You know. Okay. Okay. Oh, okay, good. So now we want to move from one state to the other. So meaning we are moving from state 0 to state 4, okay? So we can move from 0 to state B. Here is also 0. Now, if we maintain that same state, so we can move to state 4. But we know that we can actually move between 4 states. So you observe that here we have 16 bits, and this meaning 4 bit sequences repeat themselves at interval, meaning after about 4 bit sequence, let's say this, let me use this now. So it means that 1, 2, 3, 4 will most likely be in the same state. Then 1, 2, 3, 4 will be in the same state. 1, 2, 3, 4 will be in the same state. 1, 2, 3, 4 will be in the same state. So 1, 2, 3, 4. So let's get rid of that. So it means that these two will also be in the same state. So, and we said 7 steps, right? We are doing 7 steps. So it means these bit sequences will have to be in 7 steps. That's the 7-step tree, right? 7-step tree diagram. So we are moving from 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, 7, right? So, and we can move, we also know since we have 3 shift registers, we have about, the state is 4. So I move from 0 to 4. And the interval from here again, from 0 it moves to 1. And this from 5 to, from 5 to 4. So in between, we still have 4 steps, right? So these 4 bits will take on that same state. So from there, 2 to 1 to 2, then 5 to 6. So between 2 to 6, we still have 4 steps, right? So these 4, they'll be in the same step. So again, 3 to 7. So we're back to 7. So 7-step trading, 3 to 7. That's done. So this is the idea. The original state of the shift register is such that SRO1 holds 0 bits. Now, this is what we need. Let's change this. Let's use this one. So let's assume SRO1 here holds on 0 bits is 0. Then SRO2 holds on to 0 bits. Then SRO3 is also 0 bits. So if we feed in the input here as 0, the input is 0, it goes into the shift register. So it means that this 0 will move to this shift register, this will move to this shift register, and this will be discarded. What is held before will be discarded. So it means that shift register 0, we now have this input from, we now have the bit from the input, that's 0. Now, the original bit that was held in shift register 1 moves to shift register 2, so this now becomes 0. And that from shift register 2 goes to shift register 3, that becomes 0. And what shift register 3 held before is discarded. Yeah, go ahead, Olayinka. Olayinka, you can go.
Thank you, sir. Yes, sir. Sir, please, could you go over how you filled state B again, please? Thank you, sir.
Okay, we talked about the state. We have 3 shift registers. So 2 to the power of 3 minus 1 is in the notes, right? You are supposed to look up the lecture notes on block codes and convolution codes. So we say it's 2 to the power of n minus 1 to tell the number of states, where n is the number of shift registers, right? So here we have 3 shift registers. That's the power of 3 minus 1, which is the power of 2. So we have 4. We have 4 possible states. But now, we are not designing the regular the regular trailing diagram. We have the regular trailing diagram in the video too. So we are looking at the 7-step trailings. So we want to move 7 steps. Okay. Now for us to move 7 steps, it means I have to move from 0 to 1 to 2 to 3 to 4 to 5 to 6 to 7. And if I do that, I'll be somewhere at the middle, since I now have to play, or we now have to play with 16 possible code words, okay? Because at this point, we have 3 shift registers, so we want to assume we have the input block, Then we have the shift register block 1, shift register block 2, shift register block 3. So if shift register block 1, shift register block 2, shift register block 3, we hold their separate bits, say 001. So we will definitely have a bit that will feed into this input, say 1, for instance. So at this point, we'll have to deal with 4 bits, right? And we already know from our truth table, if we have 4 bits to play with as our input, then we have 2 to the power of n, which is 2 to the power of 4, will give us 16 possible outcomes, which we already did here and populated all of this. Now that we are moving between steps, we are having 7 steps. So for the 16 possible code words, so it means I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 possible code words. Now I have to move 7 steps. So if I say uh, 0, 1, 2, 3, 4, 5, 6, 7, then I'm done. How about this other quarter? So it means that I'll have to repeat each step in the trailing process. So in other words, I can play with 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, then 7, 7. I already have my 7-step training, okay, for the 16 possible code words. We could try this, probably with some system where we have just 2 shift registers, and then with the input, then we'll have 2 to the power of 3, which would be about 8 possible code words. We could design something like this and see if we could play with 7-step trailing or something else, maybe a 4-step or a 5-step trailing in that case. Now, now that we have this, we know that this is our initial state, but we know that we have 4 possible states. Okay, so it means we can move 4 steps, okay, in terms of moving state. I'll still crave your indulgence to look up the lecture notes, okay? And if we have some good time, maybe we'll just have a physical class next week if that's going to be the last lecture. Now, to clear all doubts. Now that I have to move from state A to state B, so let me move this way to state B. So it means that it should be, the state difference should be 4. So it means that I have to move from a 0 to 4. So if I move to a 0 and then to a 4, so it means that these 4 bit sequences, we have to assume the same state. Okay? Now, it's more like permutation. I have to end in the 7th step for the trailing. So now the difference here is 4. Now the difference between 1 and 5 is equally 4, right? The difference between 2 and 6 is 4. So it means I can, now the next step will be to move from a 1 to 5 for this, and then a 1 to 5 for this, okay? Now the difference there again, 2 to 6, so that's how we got this, 2 to 6. So the difference is the 4th step. Now the difference between 3 and 7 is also 4th step. So at the end of the day, you now see that we are on a 7-step trailing. So we still ended up in 7 without violating the norm. Is that clear?
Yes, it is. Thank you so much, sir.
You're welcome. So let us write this. Okay. Now, so now if, for instance, we now have to feed in our next input when it is already holding a 0, 0, 0, then if we feed in an input 1, so when that 1 comes in here, this 0 moves to this, and this 0 that was held originally moves to this, then the 0 held originally here is discarded. So it means we now have our input 1 here. Then we now have 0, 0. Okay. So that is how when we end up populating this and you realize that all of the bits here will shift. So once all of this comes in here, what was held originally will move, right? Is that correct? Is that correct? So now the shift register holds on a 0. What was held originally was 0, so that moves, this moves, so every other thing moves. So it's all zeros now. So 1 was held originally here by S3, so it's discarded. So the same thing here applies here. So when we feed in S1 with the input 1, what was held originally by the shift register 1 is 0, so that moves to shift register 2. And what was held in shift register 2 was 0, it moves to shift register 3. Now, 1 was held originally by shift register 3, that is equally discarded, right? Then the same thing applies here. We feed this input to the 0, so that moves, then that moves. So we feed this with a 1, so 0, 1. And we feed this with a 0, then 0, 1. We feed this with a 1, then 0, 1. Then we feed this with a 0, it's 1, 0. Feed this with a 1, so that's 1, 0. So we feed this with a 0, so that's 1, 0. And we feed this with a 1, so that's 1, 0. Feed this with a 0, so that's 1, 1. And I feed this with a 1, so that's going to be 1, 1 here. So then feed this with a 0, saying then these are shifted. That's 1. Then we feed this with a 1, then that's shifted, then the last one here is discarded. So is this clear? So we've populated the table. So we can now go back to our connection diagram. So it means that the output bit will vary depending on the connection diagram. So the output bit sequence will not always be the same. Okay? So this is going to be the algorithm that will run at the output level and at the input level. So it means that both the input and the output will be aware of this algorithm. So whatsoever is transmitted will be benchmarked based on this algorithm. So with this, we'll be able to decide whether what was received or transmitted is in error or was received correctly. So let us try out for output bit 1. So it's 0 plus 0. So that's SR1 plus SR2, 0 plus 0, that's still 0. So let us change our, let's use red this time. So that's 0. Now for SR, for output bit 2 is SR2 plus 3, 2 plus 3, that's also 0. Then for output bit 3 is SR1 plus 3, 0 plus 0 is also 0. Now, for this combination, output bit 1 is SR1 plus SR2. That's 1 plus 0 is going to give us 1, modulo 2 addition. Now, for SR2, for output bit 2 is SR2 plus 3. 2 plus 3, that is 0. Now, for output bit 3, it's 1 plus 2, SR1 plus SR3. 1 plus 0 is also 1. Now, for this combination, is going to be all zeros. 0 plus 0, 0 plus 0, so it's all zeros. Now, for this combination, that's 1 plus 2, this is 1. 2 plus 3, that's 0 here, then 1 plus 0 is 1. And in this case, 0 plus 0 is 0. Then 0 plus 1 is 1. 0 plus 1 is 1. And in this case, 1 plus 0 is 1. Now, please follow through in case I miss up any combination, so you let me know because we are dealing with all zeros and ones now. So 0 plus 1 is also 1. Then here, 1 plus 1 is 0, modulo 2 addition, right? So in this case, 0 plus 0 is 0. 0 plus 1 is 1. 0 plus 1 is 1. Now, in this case, 1 plus 0 is 1. Then 0 plus 1 is also 1. Then 1 plus 1 is 0. 0. Then in this case, 0 plus 1 is 1. Then 1 plus 0, 1. Then 0 plus 0 is 0. Then in this case, 1 plus 1 is 0. Then 1 plus 0, right? That's SR2, SR3 is 1. Then 1 plus 0 is also 1, right? Then 0 plus 1 here is 1. Then 1 plus 0 is 1. 0 plus 0 is 0. Then 1 plus 1 is 0. Then this is 1 plus 0 is 1. Then 1 plus 0 is also 1. 0 plus 1 is 1. Then this is 1 plus 1 here is 0. Then 0 plus 1 is 1. Then 1 plus 1 is 0. 1 plus 1 is 0. 1 plus 1 is 0. Right? Then 0 plus 1 here is 1. Then 1 plus 1 here is 0. 0 plus 1 here is 1. Then 1 plus 1 is 0. 1 plus 1 is 0. 1 plus 1 is 0. So, fine, we've got this. So the next step now is to design uh, the trellis diagram, okay, using the truth table. Okay, now we've gotten the truth table. We've been able to derive the truth table going by the discipline, going by the fundamental principles. So the next thing now is to design the 7-step trellis diagram. So we've been able to develop the 7-step truth table for Vitabe maximum likelihood decoding. Okay, so what do we do? So it's time to draw the trellis rather. Let's get the trellis done. Okay, let's just change this color. Let's do this. Now, I'd like to document the steps. So we have a step 0. Let's take it from here. A step 0. We have a step 1 for the trailing. 2. We have 3. We have 4. We have 5. And we have 6. And then we have 7. So let's place some dots. Okay, so to make things easy for me, let me draw some straight lines. I'll remove those straight lines, okay? So nothing to worry about. So I just draw straight lines here. I want to have, oh no, I don't need this. I need a straight line. I'm going to remove these straight lines. Just want us to have something looking a little nice. So I'm going to place my dots on these lines. I'm going to place my dots on these lines. On these lines. So so we have about 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 code words. I will need about 11 dots, right? 11 to 12 dots, but let me make 10 dots. 11 dots. Let me make 11 dots. So let's make the first dot here. This 1, 2. Okay. I also want something perfect. So permit me to get this out. So let's use this again. Oh no, oh no. Let's do this again. This is one. Okay, right? So, well, you already have your lines ruled, so you can just place the dots. So let's place the dots to help us design this. Um, so I'll have my first dot here. One, two, three, four, six, seven. So, well, this is pretty simple. It's just that it may be time consuming, but nothing to worry about. It's
What the man expected us to do.
So the most important thing is for you to get the understanding, because what you have to do going forward would be to run this program. So it means that in your signal processing devices, this algorithm will now have to be programmed to run at the input and output level, okay, of your signal processing, okay? Yeah. So just one. So once we have all of these dots all together, then we clean up those lines and begin to draw our query. Just want to know where the dots join. Yeah, that's why I'm doing this. Though it's not necessary, but we just want to get something straight so as to avoid any form of misunderstanding. Sure, sure, sure. Okay. Okay, so we have all our dots, uh, so we can begin. So let's remove the lines, right? What we need are the dots. Okay. So what's the next thing to do? So recall from this state that we have to move from, hmm, what color should I use? Let's change the color. To, to, hmm. So we have to move from a state 0 to state 0, and then a state 0 to 4. And because here you also observe that we have to move from state 7 to 3, and then state 7 to 7. So if we have to begin from the state 0, we have to terminate at point 0 and some other state, then two possible outcomes. Then from state 7, we can either move to some other state but terminate at the same state 7. But not so with others, okay? So we are moving from state 0 to state 0 to state 4. So it means we have to move from state 0 to state 0. These are all state 0. These are state 1, state 2, state 3, state 4, state 5, state 6, state 7. So when we move from state 0 to state 0, the code word is all zeros, right? Now, when we move from state 0 to state 4, the code word we have will be 101. So you must learn to include the code word. So we are moving from state 0 to state 0 to state 0 to state 0 all the way. And then we move from state 0 to state 4. So move from state 0 to state 4, from state 0 to state 4, from state 0 to state 4, state 0 to state 4, all the way. So this is the trailing diagram, the 7-step trailing diagram. Here's the point, state 0 to state 4, and from state 0 to state 4. And now, what are the code words? 000 and 010. So let us solve. So we know from state 0, so state 0 is 000, 000, 000, 000, 000, 000, 000, 000 here, 000, 000, 000. That's what we have. And from state 0 to state 4 is 101. So at this point, we have 101 here. 101, 101, 101, 101. So we're going to repeat the same thing. So we want to move from state 1 to state 0, and from state 1 to state 4. From state 1 to 0, from state 1 to state 0, 1 to 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 0. And now you observe that we are going to move from 0 to 4. So you observe as we continue to draw, as we continue to move from state to state, you see them closing up this way, okay? You see them closing up just this way. This just closed up here, right? You see them closing up just this way. See them closing up this way. Closing up this way. Okay? Okay. And we already know from the table that moving from state 1 to 0 is equally 0 for all the code words. So this is 000 code word, 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 000. So you have to document all of these, okay? 000, 000. And from state 1 to state 4 is 101. So at this point, it's 101. 1 0 1 1 0 1 1 0 1 1 0 0 0 0 0. So the next point, so we are done with this, and this. So we now have to move from step 2 to step 1 and step 2 to step 5. Step 2 to 1. So that's from step 2 to 1. Step 2 to 1. Step 2 to 1. 2 to 1. Step 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 2 to 1. Then we move from step 2 to 5. Step 2 to 5. Step 2 to 5. 5, 5, 5, 5, 5, 2 to 5. Okay. So from 2 to 1 is 0, 1, 1. This is 0, 6 to 1 is 0, 0, 1, 1. Is 0, 1, 1, 0, 1, 1, 0, 1, 1, 0, 1, 1, 0, 1, 1, 0, 1, 1, 0, 1, 1, 0, 1, 1, 0, 1, 1, 0, 1, 1. And from that's 2 to 1, then 2 to 5 is 1, 1, 0. So this is 1, 1, 0, 1, 0, 0, 0, 0, 1, 1, 0, 0. Right? So we're done with this. So we now have to move from 3 to 1 and 3 to 5. And you see it close up just the way we close this up. So we are moving from 3 to 1 and then 3 to 5. 3, and then 3 to 5. 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 So we just close up here then. So when you are designing and then you realize it's not closing up, then something must have gone wrong. Okay. And then if we're not running out of time, okay. And then so this and this. So, and then we now move between code was 0, 1, 1 and 1, 1, 0. So we have 0, 1, 1, 0, 1, 1, 0, 1, 1, 0, 1, 1, 0, 1, 1, 0, 0, 0, 1, 0, 1, 0, 1, 0, 1, 0, zero, 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 zero. Then we now have to move from 42 and 46. From 4 to 2, 4, no, that's the narrow one. We are moving from 4 to 2. So from 4 to 2, 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 2, 2, 2. Then from 4, we move to 6, right? Six, six. So from 4 to 2 is 1, 1, 0. 1, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0. Then 5 star. From 4 to 6 is 0, 1, 1. 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0. Then we now move from 5 to 2. We now move from 5 to 2. Right? 5 to 2. 2, 2. Down. And then we now move from 5 to 6. Close this up there. 5 to 6, 6, 6, 6, 6, 6, 6. So let us provide the code words. So 5 to 2 is 110. So this is 110. Okay, 110, 110, 110, 110. And then 5 to 6 is 0, 1, 0, 1, 1, 0, 1, 1, 0, 1, 0, 1, 0, 0, 0, 0. Yeah, someone, I saw a hand raised. Can you go on, please? So I saw a hand raised. Please talk to me. Are you clear or there's something you want to point out? Okay, the hand is down. So now we are done with this and this. So we're done with this and this. So we now move to the next step. That's from 63 and 67. So we now move from 6 to 3, 6 to 3, move from 6 to 3, 6 to 3, move from 6 to 3, move from 6 to 3, 6 to 3, move from 6 to 3, 3, move from 6 to 3, and then 6 to 7, 6 to 7, 7, 7, 7, 6 to 7, 7, 6 to 7, 6 to 7, 6 to 7. So we can now insert the code word. 63 is 101. So this is 101, 101, 101, 101, 101, 101, 101, 101, 101. And then 67 is all zeros. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. So the final state will be 7 to 3 and 7 to 7. So we move from 7 to 3, 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 move from 6, 7 to 3, 6, 7 to 3, and then we move from 6, 7 all the way to 6, 7. That's it. Then I now include the code word, which is all 101, 101 here, 101, it's all zeros too, run by the connection diagram, run by the output of the connection diagram. Okay, perfect. Good. I think we are making progress. We're making progress. So now what is left is to decode, right? While this, so now here we have the 7-step trailing maximum likely decoding algorithm. This is the algorithm. Now, and this algorithm run at the transmission and reception level of the communication process of the digital computing communication system. So we now want to check to see, using this system, this was transmitted. Probably something went wrong. Probably nothing went wrong. So here, what we want to now confirm is if what we receive is what was transmitted. And this algorithm has a way of benchmarking this to detect the error and at the same time correct those errors. So at the end of the day, we have the correct sequence. So now, what was received? So we have received sequence, received sequence here. We have 111, 110, 011, 111, 110, 110, 011, 111, 011, 000, 1, 2, 3, 4, 5, 6, 7, 8. So we want to check, okay? So the decoded sequence using the seven-step Chole algorithm. Then you will also ask to provide the pathway, okay? And the pathway, that's the path, we want to select the path with the least number of ones because the number of ones gives the path weight and also call it the Hamming weight. Okay, now we want to move from this first point. So let's look out for color that will be revealing. Oh, okay, let's use this. So we want to move from this point. Is this revealing or not? Okay. So I want to move from this point. So we have two options. So once we move from a state zero, a state zero. So it's either we go to a state zero or a state four. So we have two possibilities. So which are we going to take? So what we now do is, what the algorithm does is to benchmark what was received with the code words given that particular path. Now we have the input coming in this way. Now, once we receive the input, it's a 111. So we check for the pathway. So 111, should we go this way? This is upward. That's with a 000. Now the weight using your modulator addition is 111. So we have three ones here. So this is three. The pathway is three. Or should we go down? So we have a 111 as received. So this is a possibility, 101. So from here, this is 0, 1, 0. So the path weight here is 1. So it means that the path weight here is 3, comma 1. So let us resolve all of the pathways. So if we benchmark, okay, now let's go on. So it means that we have to go downward, right? Because that's the path with the least Hamming weight or pathway. So it means we have to trace from this point to our next state. To this point, this is the next state, okay? So it means we are now here. So it means that the originally transmitted code word was 101, not 111, using this algorithm. So it means this was received in error. So this is the correct bit sequence. So you see, now we've been able to detect the error and at the same time correct that error. Okay. There are multiple bits, right? Now from this point, we have two possibilities also. So, and now we have 111. So we can equally benchmark this. So we have 111, 111, no, 110 rather, receive. So we have either we go upward, this is 1102. So that would be 000. So the path width here is 0. So that would be 0, comma. Or we could come downward. So we have 110. Then coming downward is 011, 011. So that's 111. That's 3, 1 over 3. So definitely we're going to go upward, and that's 110. So no error in that code word. So we can now trace this, right? So we can take it from this point and go, we can take it from this point and go upward. So that's where we are. Is this clear, please? So we have gotten to this point, right? So this is the pathway. So we can also do this for this. I mean, this is 0. 1 plus 1 is 0, so it's 2. So the path width is 2, 0 over 2. So for this, we have 0, 1, 1, 0, 1, 1, 0, 1, 1. So let's check for both up. If we take the upward turn, so that's 0, 1, 1. Then the downward turn is 1, 1, 0, 1, 1, 0. So at the same time, we are having all zeros here. So then here we're having 1, 0, 1, 2. So same here, 0 over 2. So we have 0, 1, 1, right? 0, 1, 1. So it means we are still going upward. So this goes upward. And then we're going to have this. Okay? And then when we take the path width here, you see, by the time we compare 1, 1, 1 with 0, 0, 0, that will be 3 over 1, 0, 1, that will be 3 over 1. So it means we are coming downward. That's 1, 0, 1. So it means this is going to come down. Right? Again. So the next is 1, 1, 0. So here we have 1, 1, 0. So that's 0 over 2. So that's 0 over 2 pathway. And so we have 1, 1, 0. So there's no error here. So it means we are going upward. Again. So at this point, we have 0, 1, 1, that's 0 over 1, 1, that's over 2. So that's 1, 1, 0. So it means we are coming downward here. So this now is downward. Then we can have this, right? And so from this point, 0, 1, 1. So if we compare the path weight here, so 0, 1, 1, that will be 0, 1, 1, that's 2 over 0, 1, 1, 2 over 0. That's the path weight. So it's coming downward. So this is coming downward. Okay. And then we have this. So it means what we have here is 0, 1, 1. And then from this point, the path weight going upward, that will be 1. Then coming downward, 0, 0 plus this, that's 3. So it means we are going upward this time. Right? Comes this way. So it means we have 0 at this point. We have 1, 0, 1, 0. Then from this point, we have 0, 1, 1 to upward. So that'll be 0 over. If we come downward, that'll be 2. 1, 1, 0, that's over 2. So the path weight upward is lower, is lesser. So we press upward again. So slowly goes upward. Then we have this. So it means we have 0, 1. So at this point, we have 0, 0 this way. So upward is also 0 over, then the downward turn is 2, 1, 0, 1. So that's 2. So it means we're also going upward, and then it is 0, 0, 0. So from here, we can now take this upward. And then, so we can see what was decoded. Hence, we've been able to correct for errors at this location, at this location, at this point. So about 3 code words were received an error and at the same time corrected using the maximum likelihood algorithm, beta B algorithm. Is that clear? Okay. Kamiluddin, is there anything we need to explain to you? Are you still in class? Okay, it is clear now. Okay, Kamiluddin. Okay, why not talk to us? I would like to hear you talk to me. Can you unmute yourself, please? Kamiluddin. Kamiluddin, can you unmute yourself? Okay, your voice is bad. Oh, sorry. Okay. Okay, so what's the next question? So let us wipe this now. And then, so the next thing here is to provide the algorithm for converting from binary code to gray code. So we can say algorithm, oh no, the algorithm for converting between binary to gray, from binary to gray. So we already know that the left bit is the same in the gray code as in the binary, right? So the left or leftmost bit, the leftmost, left is our word, leftmost. The leftmost bit is the same in the gray code as the binary code or number, right? And then the second point is that we want to add the most significant bit, that's NSB. We want to add the most significant bit on each. So we're adding this bit to the bit. We're adding this bit to the bit. We're adding this most significant bit to the bit on its immediate. Right. And then you record the sum and neglect any carry. Okay? And then record the sum by neglecting any carry below. So the next point in this algorithm is to continue adding. It's not adding the bits to the bits on their right, and also recording the sum until the least significant bit, that is LSB, is reached. Then afterwards, the gray code number will always have the same number of bits as the binary number. That's all. That's for converting from binary to gray. And then they asked another question there to also tell the code for converting, so the algorithm for converting from gray to binary. So just like we have in the case of binary to gray, so the first point is the same. Now the leftmost bit is the same in the binary number as in the gray code. In the gray code, right? And then the second point is that the most significant bit of the binary number is transferred to the top of the second most significant bit of the gray code. And then we want to repeat step 2 for all other bits in the bit sequence. Adding the bits while neglecting any carry, right? Neglecting any carry. And then the fourth point is that the binary, just like we have in the case of binary to gray, so from gray to binary, the last point is also the same. So the binary number will always have the same number of bits as the gray code. See, that's it. That's simple. That simple. So what other question do we have now? Okay, so let's clear this now. So what's our next quiz question here? Okay, using CMOS logic, provide an explanation and the transistor equivalent design for CMOS inverter. I think that's quite simple and straightforward, but oftentimes you want to expect a more complicated design, but the principle is the same. Okay, so if you're able to get the principle where we have the P type and the N type MOSFET in play, then you should be able to analyze any complicated circuit. So here we want to design a simple CMOS inverter. So we have just a simple schematic, simple, so grounded here. And so we have VDD, and this, and so we have X coming in here, and we have Y coming in here. So this equivalent to a NOT gate, right? We'll have X and Y. And the truth table gives us something like this. So if we have a 0, then we should expect a 1 for the output. If we have a 1 here, we should expect a 0. So what's the simple explanation? This is a CMOS inverter, okay? So here, the NOT gate is designed using 2 transistors, right? As we can see, 2 transistors. So if X is the same as 1, for instance, then the P-FET is off, and the N-FET is on. Then the ground or 0 gets passed, right? And alternatively, if X is 0, then the P-FET is on, and then the N-FET is off. Then VDD or 1 gets up, because here we now have a short circuit. So it's as simple as that. Nothing more than this. So which other question do we have to consider in this little quiz? Okay, want to distinguish between axioms and theorems. They are pretty simple and straightforward.
From his videos. Now I just watching that. When I did not give it details, so there's now results.
Okay, so when we talk of axioms, you don't really need to be too complicated in your presentation. Okay, so we say the axiom of rolling algebra are usually assumed to be correct and unprovable and unprovable, while theorems are provable. And maybe, excuse me, please. And these theorems may be referred to as the laws. the laws of Boolean algebra. And then you have De Morgan's first theorem and De Morgan's second theorem. Now, De Morgan's first theorem says that the complement of a product is the same as the sum of complements. And also, De Morgan's second theorem says that the complement of the sum is the same as the product of the complement. Right? So then we have Kanoff maps and Quinn-McCloskey minimization technique. So let's write this. Then we have that Kanoff map is a graphical technique used for representing the truth table of a particular logic expression in view of simplifying the Boolean expression. Why Quinn-McCloskey? Minimization technique is an algorithm that estimates the minimum cost sum of product SOP implementation of a Boolean function. I think that's about it. And I'll say this is a good place to stop because I have to be in another review class right now. So, any question? Let's say in 2 minutes. Any question? Abiola, Emin, Matthew, Gabriel. So you can unmute now and talk to me. Are you guys okay now? Nancy, Olajide, Ezekiel. Are you guys okay now? Moyin, do we need to have one more class before, your final assessment? Moyin, Ezekiel, can you talk to me?
Yes, sir. We don't mind having a final class next week, sir.
Okay.
Thank you, sir.
Okay, so do have a great day. And bye for now.
Sir, the recording will be made available on your YouTube channel, right, sir?
Very well, yeah.
Okay. Thank you very much, sir.
Do have a great day.